Hey, good morning here. So it's Wednesday, and we'll continue on with our summer school here. But I thought I'd take some time to do a couple of announcements because we're getting to the last third of the class. This is the end of week 4. This is Wednesday of week 4. This, I guess, would be a lecture number 11. And I'll hold up the calendar here. But we are right here. We are on June 10th. And a little behind the schedule, but I think we're doing really well in the sense that we're about to finish 13 here and get started into 15. And of course, the schedule has us starting 15 and finishing 15 today. I don't think we will actually finish 15. But I really want to grab your attention to next Monday. It's come up kind of quickly. I should have been reminding you more. And so maybe I will, over the next 4 days, remind you. But you guys have another test. Your second test coming up. It's Monday. And I got to thinking about that, and I go, oh, man, it's the same structure. And I think I said that earlier. But what I should have emphasized is every time that it's the same structure. And so, in other words, on Monday, make sure your calendar is clear. On Monday at 11 o'clock, you're going to take exam number 2, okay? And it will be chapters. Is there missing something wrong?
Is it Monday or Tuesday?
No, test is Monday, yeah. Okay, so let me say it again. Test is Monday, and it's right here, June 15th. And here it is, chapters 7 through 13. So it's where we picked up after test number 1 and where we're about to wrap up today. So let me just emphasize, it would be chapters 7, chapter 8, chapter 11, chapter 12, and chapter 13. So it would be those 5 chapters. And just like the other one, there'll be a series of multiple choice. I'll probably do 4 again each. Since there's only 5 chapters, there'll only be 20 multiple choice questions. And then there'll be the normal 10 free response questions. And just like before, I'll get that ready over the next couple of days, and I'm going to ask you to check your Canvas. Make sure you see it there. Of course, when you click on it these next couple of days, Thursday, Friday, Saturday, and Sunday, it'll hopefully, say locked until 11 o'clock, Monday, June 15th. Okay, so that's the idea. Also, I still haven't done it, and I need to do it, is I'll also give you a spot to turn in your homeworks and labs for this second third of the class. And so, again, that due date will be Monday, June 15th. You'll have till midnight. Actually, the computer does 11:59. And so make sure you finish up your homework and your labs by Monday, June 15th, and you turn all those in. And like I said, you can't turn anything in yet because I haven't given you a place on Canvas. I keep trying to remind myself to do that. But it kind of caught me a little bit off guard. I knew it was coming, but it was just a little bit of surprise. And it made me think about you, that wait a minute, this might come as a surprise to you because the way this class is structured, we have a lot of learning, and then towards the end of it, we have a lot of test taking. And that's about what we're about to enter, and that's what I really wanted to warn you about. So not only do I want to warn you about the test that is coming up, test number 2, which is, again, Monday, June 15th at 11 o'clock, but after that, we get into the last third of the class, and the last third goes really, really quick. So watch what happens after Monday. Now, of course, focus your attention only on Monday right now, but let me just kind of plant the seed now and have you start thinking about after Monday, because after Monday, after you've taken test number 2, we do, of course, some more lectures here on Monday, Tuesday, Wednesday, and then we get into week 6, which we have a lecture on Monday, but then, because we're at the end, we can't have, as I've done on the other ones, 2 weeks and a test. We've got to have that third exam on that Tuesday. So Tuesday, June the 23rd at 11 o'clock will be your third exam. And that third exam will come pretty quickly because it is only a week and a day after your second one. And then right after that comes the final exam. And that would be June 24th. And again at 11 o'clock. Now on that one you'll have more time. You'll have the whole, I'll call it class time if we were face to face. And so instead of having the hour and a half plus the 15 to upload the equipment, I'll set the timer on Canvas for the whole time. And the final will be comprehensive. And it'll have more multiple choice. I probably will do the same, or maybe one or two more free response, so that the free response will be about the same number, maybe 11 or 12 instead of 10. And the multiple choice will definitely be more of them, and it'll be comprehensive. And so I didn't say too much about the final yet, but what I did want to say is just let me plant that seed. Right now, just worry about test number 2. But as soon as we get done with test number 2, we really want to start focusing on test number 3 and the final exam. And that is a way of saying after this weekend, so this weekend study for test number 2, it's really the next weekend where I want to encourage you when you have those 4 days when we don't regularly have a class, the Thursday, Friday, Saturday, Sunday, and so that would be the June 18th, 19th, 20, and 21. Those days, that weekend, so the weekend after this one, really want you to look ahead and look at test number 3 and the final exam coming on. And that's the best way you can really get ready for the end of the class, is to really free up your calendar. And that's why I wanted to say that. So if there's any way you can get your calendar free, and semi-free this weekend, because again, you have test number 2 coming up. But the following weekend, really get that free from your calendar. If you have to switch somebody at work, if you're lucky enough to still be able to work, switch with somebody so you can say, look, the weekend after I am more free and I can do a double shift there. But right now, if I could just have this time off, I could really focus on this class. Because again, a test and a final exam. Remember, the final exam is 25% and a test is another 16 2/3%. So we're not quite half, but that last week is about half of your grade. And that's a big piece of your grade. And again, rightfully so, because we spent all summer learning. Now it's time to test. Well, like I said, wanted to make that big announcement. Hopefully I didn't overwhelm you or scare you, because again, right now, let me just say it again, you have a test coming up. Focus just on that. It's test number 2. It's those 5 chapters. I'll say it again, 7, 8, 11, 12, and what we're about to finish here, 13. Okay? And so that's our test number 2. All right, so with that in mind, let me jump back and and I want to say the same thing. Again, same structure on test number 2, which includes at 11 o'clock, I will sit down, just like you in front of my computer, and I'll just keep staring at that email. And so if anything goes wrong, you have any questions, shoot me off an email. And I was really glad I did it last time. It was only about 11:02, and all of a sudden, like 3 emails came shooting in, and I was like, whoa. And we dealt with those and then got you guys started. So that was great. That was really good. And so all those issues were solved right away. And when I was answering those 3, another 2 came in. So within the first 10 minutes, I had 5 emails. Now, things seemed to go okay for a while after that, because I didn't get any emails for a while. And then later on, there were like 2 questions. 2 questions on the test where about 4 of you shot me off an email. Oh, I remember what it was, and I apologize for that. And I did that in the video of the solutions, that I tried to write 5,000, and the comma got in the wrong place, and it was a weird looking number. And so some of you thought it was 5,000, and some of you thought it was 50,000. And again, so those of you who emailed during the test, I emailed you back and say, take it as 5,000. But as you saw when I did the solutions, I graded it as, either it was more about the logic of it, not the number. And so, again, things will happen like that. But know that I'll work with you. Know that hopefully you'll feel that I was fair with you in the sense of grading it and in the sense of giving you any problem. So say it again. Anything big comes up, I'll be in front of the computer. But if it's really, really big, whatever you do, don't. I will make it right, and I will be fair to you. So know that. Don't stress too much. So now with that said, let's head back here to this chapter 13, because we've got some fun numbers to do today in chapter 13, and quite a bit still left here in 13. And the first one here is the concept of specific heat. And so, as you probably recall from the end of the lecture, we were introducing chapter 13, and it was called the thermal energy chapter. And I had a picture on the board that looked like this. Let me go ahead and put it here again. But I said, what if you had a hot object and you set it next to a cool object? And I put these blocks out here, so let me do that again. Here will be my aluminum, and I think I was using lead yesterday, and so I'll just put them together. And I said, now, if this hot object's being hot, and so I'll kind of draw a bunch of aluminum atoms here, representing here, and I'll just put Al for aluminum. So here are these aluminum atoms that makes that aluminum block. And over here is a colder piece of lead, okay? And so I'll put a bunch of dots here to represent the lead atoms. And of course, remember, they're jiggling around. And of course, the ones here that are hot have a higher temperature. So remember what we said at the end of the lecture, these would then have a higher average kinetic energy compared to these. Doesn't mean there's more energy in one versus the other just because its temperature is higher, because again, there's that total number. But what would happen then is there would be a transfer of energy, and that transfer was that word heat. I think I was using a number like 10 joules, and so the hot object might lose 10 joules, which means, according to conservation of energy, or what we call the first law now of thermodynamics, would say then that the cold one gained the 10 joules of energy. And so this loss of energy must correspond to a decrease in temperature. Whereas this gain in energy must correspond to an increase in temperature. But how much did the temperature change? So I'll say it again, remember, temperature is not exactly the energy. It's related to the energy. It's actually related to the average energy. So it would depend on how many you have, as well as what the material is. And that's the best way to understand specific heat. Specific heat is really a measurement of that material that really says this: how much heat did you give an object, or take it away, but let's talk about warming something. So how much heat is given to that object? And then per mass, per degree temperature change is a number, which is a constant number, which is its specific heat. And that's what I want to introduce you to here as we actually now get into some calculations, some numbers. What I mean by that is this specific heat. If we look at this definition, what is this actually saying? This number is saying how much energy would it take to warm up 1 gram, 1 degree? That's what this definition is saying. And so probably the best one to do is to talk about water. What would be the specific heat of water? How much energy would it take to warm up 1 gram, 1 degree Celsius? That was our definition of a calorie. So the easiest specific heat is water. Water takes 1 calorie per gram to warm it up 1 degree. So this definition, this specific heat, is again a measurement, a property of that material. And as I'll show you in a moment, it would vary from material to material. So we need to know what material we have. And I picked the water first because water is the easiest one. Water is where the definition of a calorie comes from. The whole definition of a calorie is saying how much energy does it take to warm up 1 gram, 1 degree. So the specific heat of water would be 1 calorie per gram per degree Celsius. Now again, if you remember from yesterday, we said there were many different units for measuring energy, and another very useful one is joules. So I could also say that the specific heat of water is 4.18 joules per gram per each degree. And then let's stay away from the capital C for calorie and the BTUs that we were talking about yesterday. But it might be useful to use either one. Like I said, if we're talking about mechanical energy stuff, maybe joules is better. And so, you know, something mechanical like the fall of water in a waterfall, how far it falls, is probably best calculated the energy with gravitational potential energy, which comes out to be joules. And so if you wanted to know that loss of energy then shows up at heat at the bottom of the waterfall, you probably want to do things in joules. And then on the other hand, if you're mixing things together and you have liquids and water mixes with water, maybe calories is the way to go. So we're going to do both here. It all really depends on what's happening. And so again, this is that meaning. Now let me give you some symbolism for the specific heat. The traditional symbol is the lowercase c. So let me put the C here. And for heat, the traditional symbol for heat, I think I've just been spelling it out this whole time, even way back in chapter 7 where we were talking about the heat when two things impacted. I didn't use the traditional symbol. Kind of debated in my head if I should give it to you then or wait till now, and I guess I decided to just give it to you now. So there's the traditional symbol for the heat. Now the other two symbols you're already familiar with, mass and then change in temperature. I guess I didn't even write it out in words over there. I already gave the symbol right here. Didn't realize I did that. But I like to write this equation in a slightly different form that says Q equals, and then we can write it as MC delta T. Partly because it's just easier to work with and memorize equations that aren't fractions. But partly also because when it's written in this form, it gets kind of the gist of what I'm trying to say to you, that the energy and temperature are related. They're not the same thing, right? So you have to take these three factors to figure out the total amount of energy. You know, a good example would be coming over here and grabbing a beaker. And at the moment I don't have any water in it, although in a little bit I'll fill it up. But what if there just was 300 milliliters, which would be 300 grams of water in here? And let's say it warms up or cools down, but I'll just go warms up. Let's say it warms up, 2 degrees. How much energy would that be? And hopefully you can do that formula, but also hopefully you can do it just conceptually. Because conceptually, this is what we mean by specific heat. If the specific heat is 1, we're saying it would take 1 calorie to warm up 1 gram, 1 degree. So if I have 300 grams, well, to warm up 300 grams, even just warm it up 1 degree, let alone 2, but just 1 degree would be 300 calories, right? Because that's what we mean by a calorie. It takes 1 calorie to warm up 1 gram, 1 degree. So 300 grams would take 300 grams to warm it up 1 degree. So then if you warm it up another 1 degree, that's another 300. So 300 and 300 is 600. So just the concept of the specific heat. And that's why I want to spend a little time here and make sure you understand what this symbol is, or I shouldn't say symbol, this concept, this number. What do we mean by the specific heat? Okay, so the specific heat is unique for that material. It is really telling you how much energy does it take to warm that material up. At least 1 gram of that material, 1 degree. Because you might have more than 1 gram, or you might warm it up more than 1 degree. And so it makes it a nice little ratio, or a rate, if you will. I hesitate using the word rate, because we usually save that word for time. But this is then how much per each gram per each degree. It's a little bit like saying if you're going on a trip, which, you know, most trips and flying and traveling have been canceled in this pandemic, so maybe this example isn't so good. But if somebody says, hey, you could go to Hawaii for $200, you're like, really? I can go to Hawaii for $200? Yeah, $200. You mean me and my friend can go to Hawaii for $200? Yeah. Well, it's $200 per person. Okay. So the two of us would be $400. That's still pretty good. Well, it's $200 per person per day. Oh. Well, so if I went for 5 days, I mean, for me, then that would be $200 per day. So that's 1,000. And then my friend would be another 1,000. So that's 2,000. Oh, well, see, my point is be careful about the ratio. How much is it per person per day versus what is the total? And that's what this is. The specific heat is how much. It's what in math class we call a double per. It's how much per person per day. This is how much per gram per degree Celsius. And so back to my water analogy here, or I should say away from my traveling analogy and to the real point here, to the water. If I have this 300 grams, then here's what I would do. I'd say, okay, it takes 1 calorie to warm up 1 gram, 1 degree. So all 300 of them are going to take 300 calories to warm it up 1 degree. And I'm warming it up 2 degrees, so that's going to be a total of 6. That was my thinking. And so hopefully by me going through it twice and including the little travel money thing, maybe you see it a little easier. Let's try the calculation. If I come over here, I could put in some numbers. So if I put in a mass of 300 grams, so that's what I said is over here in the beaker, 300 grams, and I put in a specific heat of 1 calorie per gram per each degree, and I put in a change of temperature of 2 degrees Celsius. And I'll focus first on the numbers. You'll see that 300 times 1 is 300 times 2 is 600. So there's 600. And a gram in the numerator cancels with a gram in the denominator, and a degree Celsius in the numerator cancels with a degree Celsius in the denominator, and it is then 600 calories. And so sure enough, both conceptually thinking about what's the meaning of the specific heat, as well as the actual calculation comes out to be 600 calories. And if I take one more step, remembering that a calorie, and I'll just do a direct substitution, change the units, a calorie is 4.18 joules. So 600 times 4.18 comes out to be 2,508 joules. So the energy needed then to warm up these 300 grams or 300 milliliters of water, 2 degrees Celsius, is going to be, and you can do it in calories, 600 calories, or you can do it in joules, 2,580. And like I said, in this case, joules is probably, calories is probably better than joules because it's working with water, and that's the definition of calorie. And that's why we like calories still. There's no mechanical energy here, so I don't think joules would be the best way to do this problem. I would just leave it right there. Well, I want to show you then a little chart in your book that you're going to need as you work through these problems. Because every material then has a different number here on how much energy does it take to warm up 1 gram, 1 degree. And so if I can find a pointer here, I've started off, and so here's this chart that says specific heat. Here's solids, here's liquids. Let me go to water. There's what I was showing you. There's water. And so water is a 1, if I do it in calories per gram. And they do it, now, instead of joules per gram, they increased it by a factor of 1,000. They did kilograms here. So that doesn't really match up with mine. I did it per gram. So theirs should be 1,000 times bigger than mine. Let me come back over here to mine. So if you multiply this by 1,000, you get 4,180, and they did one more decimal, 86. So I'm hopefully trying to point out that you can use either one here. Let me focus on the calories here, because as you'll begin to see if you scan this chart, 1 is actually a pretty big number. The specific heat of water is actually pretty high. It takes quite a bit of energy to warm up water. And there's a lot of interesting physical consequences of that. We have a fun lab to do on specific heat today, and we'll talk more about the specific heat. We'll measure it for some different metals. We'll do aluminum, and so let's look at aluminum here. And so aluminum comes out to be 0.215. And actually aluminum is one of the higher ones for the metal. Look at the copper, it's a 0.093. I don't see lead up here, but lead's really small. It's about the value of gold, and so 0.03 for gold, and that's the value of lead. So what the exact value is isn't all that important. What's important is you need to know what this number is. And once you know that number for your particular material, gold, aluminum, silver, whatever, you can then have a mathematical relationship between the energy and the temperature. Now, you'll begin to see that your heavier or your bigger atoms tend to have a smaller number. And there's a reason for that. Hopefully you can see that here in the chart. If I look over here, if I compare aluminum to gold, since they're in the chart, remember aluminum is only number 13 on the atomic table here, and the atomic number is here, and its atomic mass is only 27, whereas gold over here has an atomic mass of 197, a lot more. And basically what that means is to get 1 gram of gold, you have far fewer atoms than 1 gram of aluminum. And that's why the specific heat is so much smaller for gold or lead. Lead's not far, by the way, from gold. These are so small because it doesn't take very much energy to warm them up 1 degree. It makes sense because there's not that many atoms. Now I got to be careful with that, not that many atoms. There's always a lot of atoms to make 1 gram of gold. But the number of atoms to make 1 gram of gold is much, much lower than the number of atoms to make 1 gram of aluminum. And so because of that, you've got to give aluminum a lot of energy to warm it up 1 degree. That is 1 gram 1 degree, because you've got so many atoms that you have to make jiggle around. Whereas gold, you don't, or lead, you don't. So I'll say it again, not a real big deal what this number is. What is the big deal is that you see the chart, there's the number, and if you ever have a problem that is talking about energy and temperature and those are needed, this is the mathematical connection. And that's what I wanted to point out. Well, let me keep talking. I'll turn this off here. Because you, as I said, might come across a problem, and I know you will, a lot like I just did, when the water is warming up. And to figure out how much energy that is, you would have to get the change in temperature and the mass and the specific heat, multiply them together, and that's how much energy it would take to warm up the water. Let me emphasize that it's the same calculation when it cools down, because conservation of energy. So in other words, if I change this problem and say I have 600 grams of water here, it's 300 grams of water, and I had warmed it up 2 degrees, so that is 600 calories of energy went into here. What if I now let it cool down those 2 degrees? And so, maybe I warmed it up, because maybe it started at room temperature and I warmed it up 2 degrees. But then I left it alone. I just left it on the table and I stand back and in an hour from now it has cooled down. And so if it has cooled down by 2 degrees Celsius, it must have released that energy, and it must be the same energy. And so this, I'll say it again, is really the equation, the connection between any calculation, any kind of problem you might have that is saying, hey, how does its temperature change? How does its energy change? This is that connection. So you have to know, of course, 3 of these 4 things in order to figure out, hey, what's going on here? Now, with that said, I wanted to do maybe a harder problem here. And let's come back to this aluminum. See, this aluminum is 90 grams. This lead is 300 grams. And as I was saying earlier, what if I were to put this hot one next to this cold one? Well, then that the energy will go from the hot one over to the cold one. Okay. Now, if I told you this hot one was starting at 50 degrees Celsius and this cold one was starting at 20 degrees Celsius, and you put them together, could you tell me their final temperature? And to do that, we need to take advantage of this equation. And more than that, we need to take advantage of conservation of energy. Those are the 2 big things we've talked about so far in this chapter. Watch what happens. If I take this, okay, so here's my starting conditions. So I have this 90 grams of aluminum at 50 degrees Celsius. And I bring it next to this 300 grams of lead that are at 20 degrees Celsius. The lead's temperature is going to go up. The aluminum temperature is going to go down as energy moves from the aluminum over to the lead. But what is the final temperature? And the first step is a conservation of energy step. The first one says the Q. Remember, Q is the heat. The Q that comes out of the hot aluminum piece must equal to the Q that goes into the lead. That's what I was trying to say in yesterday's lecture. Take advantage of what we're now going to call the first law of thermodynamics. First law of thermodynamics, knowing that heat is an energy, we can use the principle of conservation of energy. Now, I suppose I should be a little bit careful here, and let me come back to this equation, because most of the time when people write a change, what they mean is take the final and subtract the initial. So final minus initial. And that's exactly what I mean here. However, if you look closely at this math, this would mean that if something warms up, you would get a positive number, but if something were to cool down, you would get a negative number, right? If it cools down, you're saying that the final temperature is less than the initial, and so you get a negative number there. And there's really nothing wrong with positives and negatives, except when I come over here, I really meant what comes out of the aluminum goes into the lead. I just meant absolute value, the numerical value. Because I am not trying to say that a positive number equals a negative number. That would be a mistake. And I could have easily fallen into that mistake. And I know students have a lot in the past, and that's why I wanted to show you this calculation. And in fact, this is such an important one. That's why the whole lab today on specific heat centers around that calculation. And just getting students to realize that, okay, if you're going to apply conservation of energy, be careful what you mean by that. You meant the absolute value of the energy. The positive number of the energy coming out is equal to the positive number of the energy going in. And if you mean that, then use the math symbols with absolute values. Because you do this calculation, you might get a negative number. And since one is losing and one is gaining, nobody would ever try to say, hey, the positive number is equal to the negative number. That would make no sense. You would try to do a calculation and it would just be some weird answer. And you'd go, well, that doesn't make any sense. Yeah, it doesn't make any sense because when you start off saying the energy leaving one is equal to the energy going in, you're really meaning the absolute value. And so that's probably the biggest warning I can give you in this calculation. Now the rest just kind of falls into place. It would look something like this. Okay, so if I take the Q for the aluminum, I would write it as MC delta T. And if I calculate the Q for the lead, I would write MC delta T. And then, of course, the other big warning I want to give you, and it's really kind of the same warning I was trying to give you in Archimedes' principle, you see an M up here and you might think, oh, they're the same M. But no, just like the last chapter with Archimedes, where we had the mass of the object and then we had the mass of the fluid displaced, and those are so easy to get mixed up, just like the density too. We had the density of the object and the density of the fluid. So easy to mess those up. And I tried to emphasize, don't confuse those.